Hi students, welcome to Mrs. Lee's Chemistry Academy. Today we're going to cover quantum mechanics. This is tied to the learning objective from College Board 1.5. The student is able to explain the distribution of electrons in an atom or ion based on data. The student can explain why a given set of data would suggest or does not suggest the need to refine the atomic model from a classic shell model with the quantum mechanical model. The student can determine whether the model is consistent with evidence given information about a particular model of the atom. Now, in the Bohr model, there are misconceptions. Although he is correct about describing the energy level for hydrogen, but it is fundamentally incorrect for other atoms. Electrons actually do not move around the nucleus in circular orbits. But the Bohr model is still of great value to us today because he has made the theory that energy levels are quantized. And that has paved the way for quantum mechanical model developed by Heisenberg, de Broglie, and Schrödinger, who used mathematical functions to describe the wave properties of electrons. So quantum number, we have described an orbital. Now orbital is really the probability of finding a fast-moving electron within the region. And every orbital is described by 4 quantum numbers. The first one is principal quantum number, which represents energy level that can go from 1, 2, 3, and up. The next one is the angular momentum quantum number described by L. And that's the shape of the orbital, which is represented by the number 0, 1, 2, up to n minus 1. The next one is magnetic quantum number, m sub L. And it describes the orientation of orbital represented from negative L to positive L. And finally is the spin of the electrons, which can be plus half or negative half. Now let's take a look at the orbital. First of all, the s orbital, which is represented L is 0 and m sub L is 0. Now it looks like a sphere. So as you can see, the 1s orbital is smaller than 2s and 2s smaller than 3s. That's because the electrons are spinning at a higher energy level, making that probability region to be larger. The next one is a p orbital that looks like a dumbbell and has 3 orientations along px, py, and pz. Then you have the d orbitals, which has 5 orientations, and it looks like 2 sets of dumbbells crossed together. Finally, there are the f orbitals with 7 orientations, and it looks even more complicated. So remember S, P, D, F in the order of 1, 3, 5, 7. So here is the diagram showing energy level, and at each energy level how new orbitals are added, and total number of orbitals at that energy level, and the total number of maximum electrons you can put into that energy level. Starting off with energy level 1, we have the s orbital, and there's only 1 orientation with 2 electrons filled. Now then we go into the second energy level, where you have the s, and introducing the p orbitals. Remember, p has 3 orientations, so now we have 4 orientation, and multiplied by 2 electrons per orbital, we have maximum 8 electrons at second energy level. When we go to the third energy level, we are introducing the d orbitals with 5 orientations. So altogether now there are 9 orientations, housing 18 electrons maximum. And lastly, with the fourth energy level, we are adding the f orbitals with 7 orientations, altogether 16 orbitals, housing 32 electrons. The Aufbau Principle is really the order of filling. How do you fill this electron? One at a time. It always goes from lower to higher energy level. It follows this order, but it may seem to be complicated, and don't try to remember it. this is an easy way. Have a periodic table right in front of you, and you color group 1 and 2 as one block. We call that the block S. Then you color your 3A to 8A as the P block. Then you color the in-between transition metals at the D block. And then finally the last two as the F block. So if you follow the periodic table in terms of atomic number, increasing one at a time, then you would know the order of filling. So here's another diagram showing the orbital energy level, and they're in different colors. Notice that the 1s is the lowest in energy level. Then you go into the 2s and the 2p, which I have colored green. And then you go into the 3s and 3p and 3d. And then your 4s and 4p. But notice that the 3d comes between the 4s and the 4p. So the way I describe to my students is that in a class, let's say you have many students taking AP chemistry, but you have the very bright 10th graders among the 11th graders. So the 10th graders can be viewed as the 3D coming in between the 11th graders. Hund's rule, which basically says that electrons will occupy an orbital one at a time if they are of equal energy, which we call degenerate, before they get paired up. So you look at 2p3, there are 3 orbitals. Not all 3 electrons would go into 2 orbitals. You would fill up one at a time before they get paired up. So in a way, if you have 3 children in a home and they all have their own bedroom, there are 3 bedrooms, 1 for each. But when you have the 4th kid, then the 4th kid will have to pair up with one of the kids. Pauli exclusion principle. That no 2 electrons in an atom can have the same set of 4 quantum numbers. That in another way it is saying that the orbital can hold a maximum of 2 electrons with opposite spin. In other words, every electron would have its own specific location, and there's no duplicate. So you can see, first we fill with the black arrow, which represents 1 electron, and then we pair it up with another electron. Electron configuration is really the way in which electrons are distributed among various orbitals of an atom. It follows 1, the Aufbau Principle, the Hund's rule, and the Pauli exclusion principle, which I have previously mentioned. To sum up, the orbitals are filled in order of increasing energy with no more than 2 electrons per orbital. Now, if you look at hydrogen atom, which has 1 electron, so the electron configuration is 1s1. The first one representing energy level 1, S meaning the shape of the orbital, and the superscript of 1 meaning there's 1 electron there. If you look at fluorine atom, it has total of 7 electrons. So the electron configuration is 2 electrons will go into the 1s orbital, the next 2 electrons will go into 2s orbital, and the last 5 electrons will go into the 2p orbitals, hence having 1s2, 2s2, and 2p5 as the electron configuration. Here's a diagram which I have placed from lithium all the way up to sodium. I have also placed the orbital diagram next to the electron configuration. So you can see with the lithium, which is 1s2, 2s1, in electron configuration, we have 2 electrons in the 1s orbital, 1 electron in the 2s orbital. And let's say if we jump to nitrogen with 7 protons and 7 electrons, the electron configuration is 1s2, 2s2, 2p3. Now you can see the 1s orbital is fully filled with 2 electrons, 2s orbital is filled with 2 electrons, and the 2ps, 2py, 2pc, each one has 1 electron. Now then, if you go to neon, then you would have total of 10 electrons, and the 2p orbitals are fully filled. Then when you go into sodium, it has 11 electrons, so that's the 11th electron will go into the new energy level, which is called the 3s1, because the second energy levels are fully filled. Sometimes you can write the electron configuration in terms of a condensed fashion. That means we will first represent the inner core electron with noble gas configuration, and then we put the valence electron in addition to it, such as sodium. If it has 11 electrons, the first 10 would resemble that of the noble gas neon. So we put neon inside the bracket, and then we put the valence electron, 3s1, on the outside. Manganese is a transition metal with 25 electrons, so we use the nearest noble gas argon, then starting with 4s2 and 3d5. Remember that the orbitals are always one level lower than where they belong in the periodic table. Now with zinc, the last element in the 3d energy level, we have argon, 4s2, 3d10. When we go to La now, then we begin to be very careful, because now we use xenon as the nearest noble gas right before La and fill up with 6s2 and 5d1. But following that, we look into the 4f orbital, because basically the 4f and the 5d are very close in energy and they should really be housed in one box, but that will make your periodic table super long and we don't want that. So we kind of take them out and footnote them. So after 5d1, you go into the 4f and 4f5 in this case. Now with the lead, we have the xenon, and then we have the 6s2, and I really hope that you have your periodic table right in front of you to help you. After the 6s2, actually we have a 5d1, and then we look into the 4f14, then we look back into the 5d to make it up to 5d10 before we fill the 6p2. Now that comes with a little bit of practice, but I'm sure you can handle this. Uranium, which has 92 electrons, then we write the Rn for the inner core, followed by 7s2, 61, 5f3. Notice the 5f and the 60 are very close in energy. When in the orbital filling, if there is an unpaired electron spin, then that substance will be attracted by a magnet. We call that paramagnetic. For example, in nitrogen, you have the 2p3. They are all singletons. They are unpaired, therefore they will attract magnet. Whereas if you have fully filled orbitals like beryllium with 1s2, 2s2 fully filled, there's no unpaired electron, they actually repelled by the magnet. We call that diamagnetic. So the magnetic properties can provide direct evidence for electron configuration of elements. Now let's look at electron configuration of ions. When an atom loses electron to form an ion with positive charge, the electrons are lost with from the highest principal quantum number first. In other words, the outermost energy level. The 4s is removed before the 3d, and the 4p is removed from the 4s. Although you may question, the 3d comes after 4s in terms of filling, but in terms of removing, we always remove from the outermost energy level first. So with magnesium, 2+ ion, after losing the 2 electrons from the 3s orbital, we are now left with neon inner core. Zinc 2+ ion, we actually remove the 4s2 electrons and leaving the 3d10 behind next to the argon. With the iron 3+ ion, we lost 3 electrons, so we're losing first 2 from the 4s orbital and the next one from the 3d orbital. So now we have 3d5 left. The tin 2+, we are losing the 4p2 electrons. And for the tin 4+, we now lose the 4s2 electrons. To summarize what we have learned today, 1, we have learned the rationale of why we need to refine the Bohr model to that of the quantum mechanical model. 2, we learned that orbitals are just probability map of finding an electron within that region. And finally, we learned how to describe the distribution of electrons of an atom by electron configuration and orbital diagrams. We're using Aufbau Principle, Hund's rule, and Pauli Exclusion Principle. I hope that you have found the video useful to you. And from the team of MLCA, we want to thank you for watching, and I hope to see you next time.